Hello everyone, welcome to another lecture of this course. So in this lecture we are going to see a isolated foundation with uniaxial moment which is causing uplift in the foundation. So how we shall calculate the base pressure for that we will be I can say learning in this particular lecture. So let's get started. So here for example, what we will do, we will take a you can say random foundation. Suppose I'm taking a foundation of around 2 meter by 2 meter dimension. Okay, so I'm obviously we basically decide the foundation dimension, but here what I'm doing, I'm taking the foundation dimension and I will check whether this dimension is okay or not. Okay, so suppose we are taking a foundation of 2 meter by 2 meter. We have the column here. Okay, we have the column here. Then if I see the axis, so here is my axis. Here also I have the axis horizontal. Sorry, let me just delete this. So it will be my horizontal axis like this, correct? So suppose this is my y and this is my x, correct? Now what I will do, I will apply a you can say vertical load of suppose 500 kilonewton and a moment about this y-axis, positive y, if you see right hand thumb rule. So this my is equal to suppose my 250 kilonewton meter. Okay, so this much load that we have applied here, correct? Now what we can do, let us draw a you can say section here, and if I just draw the section of this foundation. Okay, so this is my foundation and I am having a vertical load of P equal to 500 kilonewton and a moment of my equal to, let me just write it here, my is equal to 250 kilonewton meter. Now if this is my soil, so here not only this P is acting, also the this sulfate of the foundation is also acting, correct? So if I consider the foundation is of suppose 600 mm, so 0.6 meter, so what will the sulfate of this? It will be sulfate, if I add, so plus sulfate equal to 2 into 0.6 multiplied by 25. Okay, so let me just remove it here. So I will just write it as sulfate. So the sulfate will be basically 60 kilonewton if you calculate. Okay, so it will be 60 kilonewton. So my total P is equal to 560 kilonewton, for which we will be getting the base pressure, right? And additionally we have the moment, correct? So now if we simply find out what is the pressure that we are getting, so we have a simple formula of P by A divided plus minus M by Z, right? So if we just do it here, so we will be getting 560 by 2 multiplied by 2 plus minus 250 is my moment. Now Z value we know, Z equal to BD square by 6. Now here, as the moment is about y-axis, right? So this dimension along x is basically resisting that moment, right? So this will be my D, and here this dimension will be my P. So as it is a similar dimension, it is not an issue, but when you have a rectangular footing, so carefully you need to understand, I mean carefully you need to consider this. So it will be 2 multiplied by 2 square by 6, correct? If I just find out the Q max is equal to, so let us do the calculation here. Q max is equal to 560 divided by 2 multiplied by 2 plus 520 divided by 2 multiplied by 2 square by 6. If you just find out the maximum pressure we are getting, it is 327.5 kilonewton per meter square. And if you see the Q minimum, so you just have to use the negative value. So the negative value will be getting, we just delete this to minus, so we'll be getting it as minus 47.5. So minus 47.5 kilonewton per meter square. So here we have done the you can say linear analysis, right? So now if you see the pressure diagram, so suppose this is my foundation of 2 meter width, correct? This is the center line of the column, right? This is the center line of the column, and if you see the pressure distribution, so this is my minus 47.5 kilonewton per meter square, okay, and here I will be getting around 327.5 kilonewton per meter square. And if I draw the diagram like this, it will be something like this, correct? So basically it is this particular area is under compression. This particular width, I would say this particular width is under compression, so it is providing reaction like this, right? Linearly varying. And here basically what we understand from this negative value, that there is a resistance under the uplift, I mean due to resistance towards the uplift, or against uplift, sorry, not towards, against uplift. Now the thing is that this footing is basically resting on the soil. So if I just draw it here, that this is my footing, okay, here I have the column, and this footing is now getting, I mean it is having uplift like this, right? So you can easily understand that when we have soil, this particular area or this particular width is under now compression, right? This particular under is under compression. But soil cannot provide resistance to uplift. Soil cannot provide resistance to this particular phase to go up, right? It cannot take it down, right? Soil will be here only, so the footing is going up, so there will be no resistance here for uplift provided by the soil. So here the pressure will be basically zero, correct? The pressure will be basically zero. So what we are getting from the linear analysis, this negative value, in the real scenario, there will be no negative pressure in the foundation, correct? So generally in the linear analysis, what we consider that we have is, suppose if I talk about the software analysis, we you can say assume the soil as springs, right? And here my foundation is connected. So if the compression load is coming, so it will provide resistance to compression, right? PR. And if there is any tension, so it will provide tension resistance, I would say TR. Right, it is a linear spring. But in general, in real scenario, if you see this spring, so it will be like this, that here will be the spring. If you providing some P, it will give you resistance PR after some settlement. That's why we are providing settlement subgrade modulus or settlement value, right? And if there is any tension T, here the resistance provided by the spring under tension will be 0, correct? So for this example, let us take a net SBC of 400 kilonewton per meter square subjected to 25 mm settlement. Okay, so in the software program, we'll be defining the subgrade modulus or the spring constant using this particular value. So now you understand that the soil doesn't work the way we calculate here, right? This negative value will not come. So that means now the spring has stopped working, or the spring is, I mean, whatever result we are getting from the linear analysis or from this linear spring. So this is the linear behavior. And here what we are getting is the non-linear behavior, because though we are having uplift, but there is no resistance under for this, so it is 0. Linear analysis if we do, obviously there will be, I mean, the spring will be going up, and it will provide resistance to tension. It will be providing you the value also for the negative pressure. So here it is a non-linear spring basically. Okay, so when the footing is going under you can say uplift, then due to this behavior, the pressure that we are getting here from the linear analysis, in the real scenario the pressure will not be the same. So basically, due to the uplift, there will be a redistribution of pressure in this effective width. Okay, redistribution of pressure in this effective width, and this width will also be not the same with the linear analysis basically. I mean, we will see how much it is coming. So what we are saying, that this effective width will be resisting a higher value of pressure that which we are getting, I mean higher than the value that we are getting from the linear analysis. So due to the uplift of this particular width, okay, this is under uplift basically, correct? This is under pressure. So what will happen, there will be redistribution of pressure, and there will be increment in this pressure, and this we can do only by nonlinear analysis. Okay, so to do it by hand, if you see different books of different authors, like one very commonly used book by W.C. Tang. Okay, this is very vastly used in the industry. For basic or easy understanding, you can also see the book by Dr. N. Subramanian, or the book by Pillai and Menoncer. So you can get some easy idea about how to do that. So now if we just calculate what will be the modified pressure. Okay, so generally we have this foundation, we have a load, suppose this is my foundation center. Okay, and we have a concentric load here. We are assuming that it's a concentric load, and at this point we have a moment, right? So now if we can convert this moment to a product of this P and some eccentricity. Okay, so how to do that? That means, what I'm saying, if we assume that this P is acting somewhere here, and there is a eccentricity of this P from the center of the you can say centroid of the foundation. Okay, and this product is giving us basically this moment. So how will we be doing that? So basically it will be like P multiplied by eccentricity will be my moment, right? So if I just do it, P is nothing but 560 multiplied by eccentricity is equal to 250, my moment. Now how to find this eccentricity? This eccentricity will nothing but 250 by 560. So if we just find out how much it will be, it will be 250 divided by 560, correct? So how much we are getting? So we are getting a value of 0.446. so eccentricity equal to 0.446 meter we are getting. So this value we are getting 0.446, correct? Okay, so this is my foundation. Okay, and this value we are getting 0.446. Let me just take this calculation a different side. Sorry, Control Z. If you just take it here, yeah. So now what we want first, we want what is the modified. See, now our pressure diagram will be something like this. We know, because there will be no negative pressure, and this is the point where the pressure will become 0, and this is the point where we will get a maximum pressure which is modified. I mean, due to the uplift there will be increase in the pressure, correct? So this is my triangle, okay, of the pressure, I mean you can say the pressure diagram. So now we all know that the total force that we are getting from this triangle will act at the centroid of this triangle. So this is the reaction that we will be getting, or force from this triangle. and it will be obviously will be equal to or the collinear to this P, and will be also equal to the load that we are applying. So we can find out in a different two different way. See, what we need is this L. So basically we are doing the back calculation to find out this L, right? So suppose we will call this as my modified length or effective width of the foundation on which the pressure is acting. Okay, the total width is L, so this is my L dash, right? If I consider this total width of the foundation as L, so in this case we know this eccentricity. Can we find this value? Can we find this value? So it will be very easily L by 2 from here to this dimension is, sorry, this dimension is L by 2, and if we minus this eccentricity, so this will become my L by 2 minus eccentricity, correct? So we can easily find out this dimension. Suppose if I call it as A, so this A will become L by 2 means 1 meter minus E value is 0.446. So I am getting a value of, if I just calculate this, 1 minus 0.446. So I am getting a value of 0.554 meter. So this width is 0.554 meter. So what we know, this is my triangle. Okay, suppose this is my pressure diagram. This is my, suppose, H. Okay, here we are calling it as L dash, so I'll just name it as L dash. And here we know the CG of the triangle, it will be always at a point which is at L by 3, correct? And we got this value, this L by 3 is equal to 0.554, or L dash by 3 is equal to 0.554. So we can say that L dash by 3 is equal to 0.554 so meter. So from that, if we can find out the, you can say, can we find out the L dash value? So L dash equal to 3 multiplied by 0.554. So equal to L dash equal to, so if you can find out L dash equal to 3 multiplied by 0.554. So we can get the result of 1.662 meter. So that means the effective width which is under compression, or you can say which is under pressure now, is actually 1.662 meters. This is my width of the foundation along this dimension, along this direction, which is under contact with the soil, and soil is providing reaction on this particular plane, because the other area is under tension now, or sorry, under uplift. So what is the uplifted width of this foundation along this direction? So the uplifted width is nothing but 2 meter minus 1.662. So 2 minus 1.662. So the uplifted width is 0.34. Okay, so if I just write it here, so this equal to 0.34 meter uplifted width. Okay, there is no contact area, you can say, or this is my loss of contact with soil. So there is no contact with soil in this particular width, correct? So we find out the effective width which is under compression, or which is under you can say in under pressure. So now if we want to find out this Qmax modified, so the Qmax modified is basically given by Qmax modified is basically given by is equal to 2 into this total P, 2 into P total divided by this modified length, or you can say modified width of the foundation along the direction which is having this eccentricity, multiplied by the other dimension of the foundation. So that dimension will be taken as completely the complete value, because there is no eccentricity in that direction, as we are taking uniaxial means a moment. So now we can easily find out the modified pressure. It will be 2 multiplied by 560 divided by L is nothing but L dash is nothing but 1.662 multiplied by other dimension is 2 meter. So how much we are getting? So we are getting a value of 2 multiplied by 560 divided by 1.662 multiplied by 2. So we are getting a value of 336.94. So I would say 336.94 kilonewton per meter square is my Q max modified. Okay, so this is the final pressure that we'll be getting here. And there will be pressure which is 0 kilonewton per meter square. There will be no pressure. Okay, so now we will verify this, the similar thing in our software also. So I will just go to save. So rather wasting time in modeling and all, so what I have done, I have just already created all these things. Already you know how to do that. So I have created one footing of 2 meter by 2 meter. Okay, I have applied I can say the slab section. If you see, it is of the similar thickness of 600 mm. Okay, I have applied the loads. If I show you, display show loads, I have the dead load of 500 kilonewton, and I have a moment which is under applied under lateral case. So I have a moment of 250 kilonewton meter. So it is, see, along plus y direction, this 2 arrows, so that means it is a moment in positive y. Okay, so about this direction like this. Correct. This is my my. So now and to provide the, I can say, soil support, so we have assigned the soil spring also. If you see here, define subgrade modulus, we have applied this soil spring as soil 1 with this constant, which is basically coming from 400 divided by 0.025, and here we kept this spring as linear spring as of now. Okay, so now what I will do, I will go to the plan view and I will run the analysis. So I'll just go to run analysis. Now if I go to the pressure, and if I find out what is the pressure for this load combination, so basically I have created one load combination also. I think I forgot to show you. So this is nothing but the 2 load cases with factor 1. So this is a service combination. Okay, to check the pressure. Now if I see the pressure for this load combination, you can see here the maximum pressure we are getting is around 326.43, and here we are getting 46.8. Remember, in safe, the negative pressure means basically pressure and positive means the tension. Okay, so it is opposite to what we are doing in the manual calculation, because in case of this pressure, the footing is going downward, so that's why it is negative basically. Okay, so do not be confused with the manual calculation. So it is basically the pressure value Q max, which is 326.43, and here the Q minimum is 46.8 as per the linear analysis. So it is nearby same. 327 we got is 326 point something we are getting there, and 46 point something we are getting in the software. We got 47. So very similar value we got, right? So but this is not solving our purpose, because we are getting uplift here. If you see, up to this particular point we are getting uplift, and we know that the soil will not be providing resistance under uplift. So now we have to convert these springs that we have assigned into non-linear spring, right? So I'll just click on OK. Why non-linear? Because we want this spring to resist only compression and not tension. Okay, so we will go to define. I'll go to soil subgrade modulus, modify, and from linear I will convert it to compression only. So that means this spring will be active only when there is compression, and it will not provide resistance under tension. Okay, so I'll just click on OK. now in this case, you have to convert your loading also into non-linear. case. Okay, so what I have to do, I'll go to define, I'll go to convert load combinations to nonlinear uplift cases. I'll click on this combo 2 which I have created, and I'll click on OK. So you can see this combination is converted to a nonlinear case. So if you see here, define load cases combo 2 nonlinear. So it is a nonlinear static case. Okay, allowing uplift. So allowing uplift means this particular area will be going, I mean, it will not be in contact with the soil. Okay, so, and the spring will not provide any resistance for this, so there will be loss of contact. There will be no pressure also in that particular location. So what I will do now, I will run the analysis, and here you can see, if I just go to the pressure diagram now for the same combination 2 apply, here you can see the pressure has increased to 336 now. What we have got from the manual calculation is also 336.94, and here we are getting some value of 336.2 or something like that. So it is very nearby value that we have got in the manual calculation and in the software analysis. And here you can see where we had earlier the pressure, positive pressure, I means the for the uplift, now it is 0. That means there is no pressure acting in the foundation up to this particular point. And if you want to find out this width up to where the uplift is happening, so this width basically, how to find this? We have already calculated manually some 0.34 meter. So if you see here, let me just mark it here. If you see this x value here, only x value, okay, so because this direction is x direction for us, so I will see this coordinate. This coordinate is x equal to -1. So here I would write x equal to -1, and here what is x equal to, how much we are getting? So if you just take your cursor to this grid, so you can see it is -0.7. It is -0.7. So what is the difference between these two? The difference is nothing but 0.3 meters. So we are also getting the similar value, 0.34 or 0.3, like that, correct? So this is how you can analyze a foundation when it is under uplift for a for eccentricity along one direction. Eccentricity means that we have calculated, if you see, equivalent eccentricity and load product to convert the moment into a, I mean, like this, P into eccentricity. Okay, so if you have uplift along one particular direction due to this uniaxial moment, right? So in this case you can use this method to check the software analysis manually also. And it is, I'm talking about isolated foundation, okay? And in the industry, when we have eccentricity about both the axes, that means you have moment about x, moment about y, and for that eccentricity is coming somewhere here. I mean, not here basically. I will draw the foundation. Suppose this is my foundation, this is my axis, and it has moment along this direction, moment about this direction also. So the eccentricity will be somewhere here, and due to which the maybe foundation uplift will be like this. So such cases, I mean, when you have biaxial moment, okay, and in such cases when you have uplift, so we generally use the chart or the curves given by the W.C. Tang in his book. Okay, so if you see here that generally, you know that we do not allow more than 25% uplift in the you can say foundation. So if you see this Tang's chart or Tang's curve, so this is the line, which is defining basically 25% uplift. Okay, this is the line which is denoting 25%. So beyond this we do not allow basically. Okay, so these are the modification factor for the moment, sorry, for the pressure. So from there you will be finding out the K value, and you will be multiplying with generally our pressure, then you will be getting the modified pressure generally. Okay, so this thing we will see later. Today we have discussed regarding the you can say uniaxial moment, and for that how we will be calculating the modified pressure, and we have also seen how the software is giving the result basically. Okay, so I hope this is completely clear to all of you. If you have any doubt, you can always ask me in the chat box or in comments, so that I can solve your doubt as soon as possible. Okay, so thank you and see you in the next lecture.